Hello students, in this video we'll consider Airy's differential equation. The Airy differential equation has the form y double prime minus xy equals 0. And so this is a second order linear. It's second order linear, but non-constant coefficient. And so we're going to have to use the method of power series to solve this differential equation. And so what we're going to do is the following. So x equals 0 is an ordinary point. And that allows me to write the solution y as the sum. K goes from 0 to infinity of some coefficients ak, x to the power k. Okay? And if y is given by this, we know that the standard idea now is to differentiate y prime is going to be the sum. K goes from 0, really 1, to infinity of k, ak, x to the k minus 1, and y double prime is the sum. K goes from 0 to infinity of ak, k, k minus 1, x to the k minus 2. Like that. Good. And now we feed this into the differential equation, right? So my y double prime becomes the sum. K goes from 0 to infinity, really 2, of ak, k minus 1, x to the k minus 2. That's my y double prime. And then minus x times y is going to be the sum. K goes from 0 to infinity of ak, x to the k plus 1, and that's equal to 0. Now I have two series that are out of sync with each other. The indices are in sync, but the powers are out of sync. So I have to put the powers back into in sync, put them in sync, and then shift and equate the coefficients. So let's do that. So the first thing we do is we recognize that really when k is equal to 0 or k is equal to 1, there's nothing there. So this sum is really nothing more than just the sum. K goes from 2 to infinity of ak, k minus 1, x to the k minus 2. Things start at 2 in this sum over here. And then what I'll do over here is I'm going to subtract to get things back down to x. So I'm going to do something where this is the sum. K goes from 1 to infinity. And then I add 1 here, so I have to subtract 1 here. ak minus 1, x to the k, and that's equal to 0. Great. Now I will shift these terms to make them in terms of x. So what I'm going to do is I'm going to now add. I'm going to subtract 2 over here and add 2 over here. So this is the sum. K goes from 0 to infinity of a k plus 2. K plus 2, k plus 1, x to the k, minus the sum, k goes from 1 to infinity of a k minus 1, x to the k is equal to 0. Now everything is going to have x to the k in both terms over here, but this term starts at 0. So I'm going to plug in 0 first, and I plug in 0, I'm going to have an a2, a 2 times 1. So this is really equal to 2a2 plus the sum. K goes from 1 to infinity of ak plus 2, and then k plus 2, k plus 1. And now, both sums start at 1 and have x to the k, so I can group the terms together. Then I have minus ak minus 1, x to the power k is equal to 0. Now I have a power series, all that is identically equal to 0, which means the coefficients have to be 0. So this is going to force a2 to be 0. There's no a2 terms. a2 is equal to 0 for the area equation. There's no x squared term in the area solutions. And then we're going to have what? Then these terms have to be 0. So that says what? That says that ak plus 2 is ak minus 1 over what? Over k plus 2, k plus 1, like so. Okay, great. So that's our recursion relationship for k bigger than or equal to 1, right? K bigger than or equal to 1, okay? So now I have two sort of classes of solutions that I'm going to get for this. So first I'm going to look at the class that starts with a0, right? So let's look at the a0 class, okay? So I can look at, for example, when k is equal to 1, I can conclude, so there's two solutions. When k is equal to 1, we're going to have a3 is going to be a0. I plugged in k equals 1, 3 times 2. 3 times 2, like that. Great. And then what? And then then when k is equal to 2, we'll have a5 is equal to a3 over what? So I plug in the 3 over here. That's going to be a 5 and a 4. A 5 and a 4. So when I plug in 3 over here, I'm going to get a 5 times 4. So A5 is going to be, when k is equal to 1, we get a 1 and a 2. So we get a 5 and a 4. Okay, great. All right. And let's see over here. Then when I plug in k equals 5, that gives me down to a, when I put 3, that gives me a 2. That's really a 2. Good. All right. And so now we have, now we want to do A6 actually. I'm sorry. So this is going to be A6. Let's do A6 rather. So what's A6 going to be? So if I want to do the A6 term over here, A6. A6 is going to be what? That's plugging in 4. So that's going to be an A3 over what? A3. So I plug in k equals 4, get an A3, and I get a 6 times 5. I have to skip the 4s. That's the whole point behind this, right? And so in general, we'll do one more over here. We're going to see that A9, that's when I plug in k equals 7, is going to be A6 over what? Over 9 times what? 9 times 8. So I skip the 7s, okay? And so when we get these terms over here, so we're going to have all the 3 terms are going to relate to A0. And so what can we say? We can therefore say that one solution, y1, is going to be A0. And then the sum of what? I'm going to have a 2, so we're going to have x to the power 3k. So we're going to have an x to the 3k. And then a what? And then k goes from 0 to infinity over what? We're going to have a 2 times 3 all the way down to what? All the way down to 3k minus 1 times 3k, like that. That's the one solution of the Airy equation, okay? And so let's check to make sure that this works. When k is equal to 1, we're going to have what? When k is equal to 1, we're going to have the A0 term. When k is equal to 0, we're assuming that this factorial over here is just going to be equal to 1. So when k is equal to 0, I have A0, perfect. When k is equal to 1, we're going to have x cubed, and then a 2, and then a 3, perfect. And then when x is equal to 2, we're going to have a 6, and it's going to be a 2, 3, and then a what? And when we plug in up to 2, we're going to have a 5 and a 6, exactly. So that's going to be one of our solutions to the Airy equation. And what's the second solution going to be? Now we're going to start this. We're going to start to see when we get to 1. So how do I get to 1? I'm plugging in a 3, right? So I have to get to A1. I get to A1 over here by plugging in k equals 2. So A4 is going to be what? It's going to be A1 over what? When k is equal to 2, I get a 4 and then a 3. 4 and then a 3 like that. Good. That's when k is equal to 2. When k, then we go up to what? Then we have to skip a couple. We go to A7, right? So what's A7 going to be? That's when k is equal to 5. It's going to be an A what? When k is equal to 5, I have an A4 up top here, and then what in the bottom? And then when I plug in k equals 5, we have a 7 times 6. 7 times 6. And then what will the next one's going to have to skip 3, go to skip 3, go to 10, right? That's going to be what? That's when k is equal to 8. So I'm going to have a 7 over what? When I plug in k equals 8, this is going to be a 10. And then times a what? 10 times 9. Okay? And so we get a secondary solution from this. So we're going to have a y is equal to, y2 is equal to, let's do a1x plus the sum. And then we're going to x to the 3k, x to the 3k plus 1. Like that. Because 4, 7, and 10 are 3k plus 1. We're going to say k goes from 1 to infinity, like that. So I'm going to start where? I'm going to start at 4, right? So you can see a 4 times 3. So we're going to have a what? A 3 times 4 times all the way down to 3k, and then a 3k plus 1 like that. And that's the second solution to the Airy equation. So I have these 2 linearly independent solutions to the Airy equation. And in further videos, we're going to see that when these are over here in the negative axis, when x is negative, these things are going to oscillate when x is negative, and they're going to grow to infinity when x is positive. So we're going to understand the asymptotic behavior of these solutions to the Airy equation when x is either negative or positive. When x is negative, we can see when x is negative, we're going to look like either a sine or a cosine. And when x is positive, we're going to look like a hyperbolic sine or cosine. So we have growth when x is positive and oscillation when x is negative. Thank you very much.